Okay, all yours, buddy.
Okay. Well, greetings, folks. We appreciate your joining us today with threatening weather outside. Hopefully everybody's safe and sound, and this will be an opportunity to get our minds off other things here and expand our scope a bit in the area of perforating, what the future holds, some of the challenging areas that exist at present. And we've got a dynamite crowd that I'm quite confident is going to lead us to those answers. So before we do anything else, before we get to the questions, I'd like to introduce our panel for this ProTech talk. I'll begin in no particular order. I'll begin with North Dakota's finest here, Kyle Haustveit. Kyle is a professional engineer. He currently is a completion engineer in the centralized subsurface group at Devon in Oklahoma City. He's a graduate of Montana Tech with a bachelor's degree in petroleum engineering, and from the University of Oklahoma with an executive MBA in energy. He's authored a number of SPE papers, a number of SPE presentations, and he's involved in a number of SPE committees and has been very active in the SPE for a number of years now. So Kyle, welcome. Glad to have you. Next up is Mr. Dave Cramer. Dave is a senior engineering fellow on the ConocoPhillips Global Completions Engineering staff in Houston. Dave, if there was a woman in that role, would she be a fellow, or would she be a lady, senior reservoir or senior global completion lady? I'm just curious.
She would be a fellow, buddy.
Still be a fellow. Okay, I gathered that. He specializes in hydraulic fracturing. He's got 42 years of industry experience. He's published 55 technical papers and holds 2 U.S. patents. He's been a distinguished lecturer for the SPE and a distinguished member of the SPE in 2019, which is a great honor, and region director in the past for the U.S. and Canada Rocky Mountain region. So Dave, great to have you, fellow, as always.
Thank you, buddy.
Next up is Phil Snider. Phil is currently retired from Marathon's technology organization. He retired about 5 years ago. He didn't really retire. He just retired from Marathon. He's busy as ever. When at Marathon, he worked mostly on perforating and downhole completions and all sorts of inventive ideas that his mind was constantly coming up with. He's a past chair of the API subcommittee on perforating and has approximately 50 patents. And currently, he's the president of his own consulting business, PM Snider Consulting, and very inventive, very creative guy. So Phil, as always, great to have you.
Yeah, thanks for the kind words.
We want to take advantage of that creative mind today for sure. Next up is Shaun Geerts. Shaun has been with Core Laboratories for approximately 9 years. He's currently with the Owen group, the Owen business unit. He's been involved primarily with perforating and other ballistic products for most of those 9 years. He currently leads the testing solutions group within Owen. He studied at New Mexico Institute of Mining Technology, where he earned a bachelor's degree in mechanical engineering and a master's degree in mechanical engineering with specialization in explosives engineering and a master's of engineering management. So he's definitely a master. And last but not least is Chris Squires. Chris is the regional engineering advisor for ProTechnics, another Core Lab division in Pittsburgh. He focuses primarily on helping oil, gas storage, and injection well operators make better decisions in their projects using completion diagnostics. He started in the oil field in 2007 after graduating from Penn State with a degree in mechanical engineering. He's worked as an engineer for Halliburton in the Northeast. And after that, he worked as the senior completions engineer at Console Energy in Pittsburgh. And most currently, he is a region engineering advisor for ProTechnics, where he does a lot of work in the Marcellus and Utica shales. So welcome aboard, Chris. Great group, guys.
Thank you, buddy.
Okay, let's start off with our first poll question. Can you pop it up there? Derek?
Yep, coming your way right now.
Okay. For those of you who are in attendance, we want to thank you for joining us, and we want to involve you, engage you in the process here. So one of the things we're going to ask for your engagement is to participate in this poll. So this is the first poll question. What is the most important factor when designing a perforating scheme? I know you're going to say, oh man, just one? Yeah, we're saying just one. The most important factor: cluster spacing, planned rate, hole size, perforations per cluster, perforation location. Okay. All right, having gotten that poll question in front of us, let's move into the first discussion question.
Buddy, you want me to leave this open and we'll come back to it when you're done with this question?
Okay, that sounds fine.
Okay.
All right, continue to think about that poll question, if you will, while we pose this question to the panelists. In no particular order, and again, as we've discussed previously, every panelist doesn't have to try to answer every question. So if you especially want to address a certain question, signal to me and we'll make sure you get a turn at it. So the first question: describe an efficient perforation. Now, keep in mind, most of these questions have been submitted by those who are in attendance, who RSVP'd. But one of the questions that came up on a number of occasions was describe an efficient perforation, and describe how I, the person who is submitting this, should go about determining the optimum hole size, penetration, and phasing for my unconventional reservoir completion design. So what's an efficient perforation? How do I go about? What's the thought process I should go through in determining the optimal hole size, penetration, and phasing? And finally, should I factor in perforation damage and cement quality in that process, that thought process? So if you can remember all those details, who wants to kick this off? Who's ready to help them consider the most important issues that they need to be considering here? All right, I saw a grin there.
Hey, Ed.
Okay, Dave, you're on.
Thank you, buddy. So regarding first the back end of that question, cement sheath and the like, I mean, what the perforations are going to control is outflow from the wellbore. So yes, cement sheath quality and all are important, but really don't per se impact very much the optimal perforation. I think an optimal perforation is one that is as per design. So we've done presumably with the perforating company tests, and we have a good idea what the performance should be, and that perforation achieves that performance. And then it behaves well with all the other perforations. So you want that perforation to have the same hole diameter. Trying to play around with variable hole diameters at a given frac stage is, I would think, a path to failure. I wouldn't recommend it. Try to get things as even as possible. And also from a gravity perspective, which kind of leads one to, an oriented perforation scheme. Again, that's combining that perforation with all the other perforations. You want that perforation in terms of, tunnel. We don't think that tunnel length is particularly an element, but having a nice communication to a frac system in the cement, I believe, is important. That gets into the tortuosity element, which is a behind the pipe factor that's very important. I mean, we don't grow these fractures in horizontal wells, in the vast majority of wells directly out of the perforations. They got to go through a starter fracture, which may be in normal faulting environments at the top and bottom of that hole, inclination wise. And then they go out a certain breadth. Various work in DTS and the like has shown that the breadth, and maybe even with, ProTechnics and tagging proppant, that breadth can extend out for 10 plus feet on either side of the perforation. So quite a pathway for tortuosity. And so you want a good crack to initiate. You're probably going to need to do some additional things to condition that flow path to make tortuosity not an element in skewing your allocation. So those are just some ideas, and I'll let others speak.
Okay, anyone else want to jump in on creating an efficient perforation? What considerations go into it? All right. Yes, Phil.
I'm pretty much on target with Cramer. I'm leaning more that phasing doesn't really matter from a step rate analysis, but I'm trending more and more to fewer, bigger holes for a bunch of reasons. So, if you look at the way the guns we've used in industry classically have been, when we started shooting lots of clusters, the shape charge manufacturers just made them shorter, but kind of kept the spiral patterns and that. So I think in general, you're going to see people migrate more towards fewer, bigger holes for a number of reasons. Why, I'll make this up, why shoot a bunch of 0.30 holes if you could shoot half as many 0.45 holes that are closer together?
Okay. Thank you, sir. Thank you, Mr. Cowboy.
Buddy.
Forgot to mention that Phil is a University of Wyoming Cowboy, and Dave Cramer is a Rutgers Scarlet Knight. You didn't put it in your resumes, but I happen to remember those things. So who's next?
I'll take a stab at a couple more, buddy. I think
Okay.
Dave, Phil hit on some key things, but on the phasing side, or on, like Dave said, getting uniform hole size, one way to do that is to try to shoot the same direction. So we try to shoot a lot of zero rephasing. I personally prefer high side for increasing the likelihood of having good cement behind pipe to create some isolation between different clusters. I also think, when we're trying to shoot equal hole size charges from the vendors, but with different carrier sizes and different IDs of casing, it can have a big impact on the actual shot size, high side, low side, or side to side. For optimal perf friction, I think that's a function of the rating of your casing, your horsepower contracts. You want to try to use as much of the horsepower as you're paying for. So I think to optimize that, you need to know the conditions of your casing and your contracts.
Very good. All right, well, moving on to a related subject, and the rest of you might want to jump in on this. Having talked about some of the key parameters that go into a perforating scheme, another question that was frequently asked, and this particular question was asked by someone who's very much involved in one aspect of perforating now. I'll just ask one of you, just anybody. Shaun, I realize you work for Owen, but if you were an operator, what would be your currently preferred perforating scheme, including orientation, and when might you deviate from your base plan? In other words, the time has come. I don't need you to go into all the discussion about how and why and all that. Just, it's time to pick your preferred perforating scheme, including orientation. What would it be?
Based on what we've seen recently, we would probably follow what the other guys have talked about, 0 degree, probably oriented upwards, probably 2 to 3 shots per cluster. And then based on what your breakdown you're looking for, target a hole size that works for what you're needing for your pressure drop and your horsepower and all of that. Target a hole size around what works best for you.
Okay. So you're a 0 degree, 12 o'clock kind of guy. Is that what you're saying?
Getting more that way every day.
Okay. All right. Some of the rest of you, again, staying on this basic subject. How do you determine the optimum cluster spacing and stage length? if you've decided what your shot density is going to be and your phasing is going to be. Dave, let's get back to you. You're an old frac guy for a long time, not an old guy, just a frac guy for a long time. How do you determine the optimum cluster spacing and stage length?
Well, so that's going to
Assuming
be
unconventionals,
right. So that, yeah, we're going to have to rely on trial and error well performance. I mean, you can model it, but that's how ConocoPhillips has addressed this over the years. You know, we have pilot projects, and we, you know, in Eagleford, for instance, started out from 50+ foot cluster spacing to 35 to 25 to 20 to 15 to 10, and then backed up. It looked like we went too far. And there are some diagnostic processes that ConocoPhillips has done over the years. I'm authoring a paper with several other guys called pump down diagnostics. It helps us get an idea of the tendency for communication between clusters when you get too close, when that communication, remember, you got these longitudinal starter fractures, so even with good cement sheets, eventually you're really going to see some pretty significant interference. And so, in my opinion, it's really tough to justify the stuff we're dealing with, and there are people who may disagree with me internally, more than 15-foot cluster spacing. But we can see in certain plays an advantage to that. In other plays, we haven't, and we have wider cluster spacing. As far as length, I think things get a little dicey once you, get beyond 200 feet of length. And I base some of that based on the old days in vertical well limited entry treatments in the Piceance Basin, where we did a study. And even with equivalent pressure drops and the like, same perforation, initial perforation friction, just had better results as we shrunk that length down. And I can't back that up from a production standpoint, but from an efficiency standpoint and looking at some of the special studies we've done of limited entry pressure drop and uniformity of erosion and what have you. I kind of like that as a maximum, and we go beyond that sometimes. So not everybody agrees with that.
Right. Thank you, sir. Chris Squires, you've been operating in the Marcellus and the Utica, a lot of gas reservoirs, maybe back in your console days. What would you describe as your preferred perforating scheme, including orientation?
Well, in the Marcellus and Utica, I think there's been some early illustrations, let's say, that suggest there's a great deal of fracturing, not just in a planar direction, but along the length of the wellbore too. So early on, it wasn't uncommon to have, like we were talking about earlier, 60-foot or 50-foot cluster to cluster spacing. Because the thought was you're getting longitudinal fracturing anyway, so you want to keep the clusters a little bit further apart. And if you get them closer together, they're going to start competing with one another, and there's going to be stress shadowing effects that make putting a stage away more difficult and getting the planned amount of sand in the ground away a lot more difficult. But that doesn't seem to be the case. Throughout all the trends that I've seen, it doesn't seem to be any more difficult to put a stage away with tighter cluster spacing versus cluster spacing. And I'm sure there's a lot of reasons for that. And the stress shadowing, it makes sense from a solid mechanics standpoint, but when you translate the actual reservoir as a composite that you're bringing to failure and you're actually breaking that rock, I think, and based on some of the evidence that we've seen lately, the tighter and tighter cluster spacings are proving successful. I think where they start to go wrong is if the treatments aren't large enough. So if you double the amount of clusters you shoot, but keep the same job size, you might not be getting the same frac length and frac height that you desire. So There's a fine blend of things there, but to put some actual numbers to things, I think in the Utica and the Marcellus, 15 clusters treated in the same stage isn't out of the question. I'd be willing to bet that you could treat almost all of those clusters with sand and have sand around almost all of those clusters in a single stage, as long as you're using limited entry or extreme limited entry. At a minimum of 2 barrels per minute per perf with about a 0.42 inch perf diameter.
Okay. Here's a
But
check. Yeah, go ahead.
I add to that, I think so on the cluster space, and I think that's an integrated discussion with geo, so you know your perm, with reservoir to understand the value of accelerant recoveries, you tighten clusters. So I think that's an important one for cluster spacing. For cluster, or for stage count, I think that's driven by the available rate. So there's a minimum rate we need to maintain with inside our casing to make sure we keep the sand suspended. 4.5 to 5.5, you're in that 5 to 7 barrel per minute range at that last cluster, so you can try to limit the likelihood of proppant settling, smaller mesh proppant settling at those rates in the pipe. But like Dave said too, the risk of having a runaway cluster, or the risk of that runaway cluster having a big impact on poor well performance, increases the longer you stretch that stage out.
Okay, one of the chat questions that has come in. What are your thoughts on using fiber warm back data and the number of fracture injection points in helping determine the optimal cluster spacing? Anybody want to tackle that one?
I like the work Conoco's doing where they've taken it a step further and integrated the DAS along with the DTS. I think temperature alone provides good information, but if you've done downhole camera work, it's pretty common to shoot base holes after your last stage to get an idea of what an uneroded perforation would look like. And we've had DTS PLTs ran across stages like that, and we try to keep it as, as generic as possible. So we don't always tell the vendor that we didn't pump through that stage. So they'll come back and allocate a lot of production to that stage that was never pumped through. So I think using DTS along with DAS to try to understand how much flow is coming from a cluster and tying it back to perf friction, erosion, it's a great workflow.
Yeah, I'd echo that. I mean, I like DTS. I think it provides good information on the breadth of fracturing activity. It's tagged to that one cluster. But yeah, distributed acoustic sensing is probably going to give you a better quantitative answer. And all these diagnostics have some issues. I mean, the measurements are based on flow through an orifice. You've got significant annular flow. That's going to have an effect on noise, but not as the same kind of effect on the intensity of the noise. So, it just depends on how accurate that's going to be. But that seems to be more, as Kyle noted, closer to how much stuff goes through a particular perf cluster.
Chris Squires mentioned about stress shadowing. Do the rest of you consider that as a considerable factor when you're working on your perforating scheme? Any potential stress shadowing effects that you might have? Does that enter into your thought process when you're developing your perforating scheme?
I'll take that one, buddy.
Okay.
I'd say a few things. Yeah, we're trying to consider stress shadowing. We're trying to get people to do things like if they're using the ball in place technology, pressure test the plug, but then shoot the first cluster and try to do a quick injectivity to try to understand stress levels before you shoot all the clusters. But I think most of the designs we see is people shoot the same thing in all the clusters in a stage. And I think that probably is a mistake. You probably should vary hole size per cluster. And then as you move up the well, you're gaining about 1,000 PSI, 1,500 less friction. So we see people do the same thing up the whole well, where you have to ask, why don't you start adding a cluster or two, depending on your contracts, and you can drop a stage or two as you gain the benefits of the increased, well, you have less friction, so you should be able to jack your rate up and put the same through each cluster. But I think we shoot it all the same thing to make it easy on the guy loading the guns, but I don't think maybe that's wise. And for the optimization process, we're learning a lot just with step rate testing, before and after step rate, or even after step rate, to try to figure out perf efficiency versus tortuosity, because anything we can do to get rid of tortuosity, is worthwhile. So that'd be my 2 cents on some of that.
Okay.
I might say something. I mean, we embark on triple zipper programs and we're developing, pads. And part of the reason for that is it gives a greater chance for pressure to dissipate in the just created fractures in a given well. That's going to lessen the stress shadowing from the toe side. On the other hand, a lot of these fractures from the side wells, depending on well space, you can grow into your domain of the next stage to be treated in a given well. So you can get some unexpected stress shadowing from the side. It's not always a toe event where it's worse at the toe and then gets a little better as you go towards the heel. So one needs to consider that. Based on that notion, and the fact that we're usually shooting a lot of clusters, I'm typically in favor of keeping everything the same number of perforations in all the different clusters, and same diameter and the same inclination, 0 phase, and as big a perforation as I can get away with as few perforations.
Okay, let's look at the poll results for question number 1. You want to throw those up there, Derek? Let's see how the audience. Cluster spacing and planned rate seem to have won the day here, more so than hole size or perforations per cluster or perforation location. All right. Kyle has posed a question to the rest of the panelists. What is more important to optimize, cluster efficiency, pressure differential, or rate per cluster? What is more important to optimize cluster efficiency? Is it pressure differential or rate per cluster? And if it's pressure differential, why don't you throw up some optimum pressure differential?
Well, so we have 2 choices, Kyle, right?
Different Kyle.
Oh,
it's not you? Oh, okay. No, Kyle. Sorry
Well,
about that. Didn't have a last
if we
name.
have those 2 choices, yeah, I would say pressure differential. I mean, rate per perforation or per cluster. I mean, heck, that's important from a fracture geometry standpoint, but from perforations, what kind of perforation do you have? Is it 0.05? Is it 0.03? I mean, it's really all about the pressure drop in my mind, and being able to predict that and maintain it reasonably. And when you look at all that, you can get too much differential pressure. More differential pressure aggravates erosion. So there's some kind of happy medium there. On the other hand, more differential pressure helps with equilibration, where you have differential bottom hole fracturing pressures tagged to all the different perforation clusters due to stress shadowing or whatever. So there's some kind of happy medium. Nobody never knows exactly what that is, but it certainly has curtailed ConocoPhillips from getting into extremely high pressure differentials, because that's when you're going to start to see big old holes being eroded in perforations. You can really overdo that. There is a happy medium.
All right. Speaking of, let's throw up that next, may not be the next poll question, Derek, but the one about the optimum delta P. Can you throw that one up? We'll get the audience to try this one. What is the optimum delta P for a given frac stage? Dave was talking about how you need to moderate that a bit, not get too carried away. You may exacerbate your whole erosion issues. We're going to talk about erosion a little bit later on here. But for now, let's vote on what is the optimum delta P for a given frac stage. Of course, a lot of this has to do with if you're going to do limited entry or extreme limited entry, or what your thinking is there. And you're right, this does depend on, somebody chatted in, it does depend on so many factors. but just in general, what would be a good target? Okay, let's move on. Next question, kind of change subjects a bit here. What is driving some operators, let me get out of the poll question here. What is driving some operators to prefer and some to avoid oriented guns firing 0 degrees phased? We had some individuals asking, why do we see an increase in, or a preferential increase in oriented perforating, and some saying, why are we getting away from it? And what about oriented perforating for mechanical isolation refracts? So let's touch on oriented perforating a bit. Should we be going to it more often, less often? What about the application of mechanical isolation refracts?
Hey, buddy, I'd like to start with this one.
Okay.
In regards to the 180 perforating versus a standard, let's just say 60 degrees, I think that there were plenty of studies done in comparing the two, both on a production standpoint and the ability to put away sand or fracture with lower pressures and higher rates. And it seemed to be the case to me that many of the operators, at least up here in the Northeast, came out of favor with the 180 because they cost more money to perforate with 180, and they weren't able to see well-defined benefit from either lower treating pressures, higher fracturing rates, or better production. No, that was some time ago with less sophisticated technology. Most of it was just an off-centered weight bar used for the 180s. And it was also when limited entry was just starting, and that was just the standard. Now the extreme limited entry is becoming more of a standard. What's happening is you're limited to only 2 or 3, sometimes even fewer perforations per cluster. So now that you only have 2, 1, or 3 perforations per cluster, people are spending more time and money to make sure that they are orienting properly. And as it was mentioned before, I think high side is the way to go, especially if you're only going to have one hole. Like Kyle mentioned, the cement is probably going to be better on the top side of the pipe. Another consideration too is that if your sand does start to settle out during the treatment, it's going to settle out on the low side of your pipe, and that's going to be more difficult to, in case you were getting close to approaching a screen out condition, it's going to make things more difficult if your holes are on the bottom of the pipe and your sand's going down too. So I like the holes on the high side of the pipe. And also there was something about the refracturing, I think you asked.
Yeah, refracts.
As far as refracts go, I think they can be successful, but you have to have the perfect candidate well. I think it just seems to be the case that people would rather put their money into a new well than put it into refracts. But if you do have that perfect candidate, it's always good to not spend as much money and get a pretty good return on it.
Would you tend to use oriented perforating in those applications?
I would say if you had oriented perforating and on the original completion, or if you had a sleeve system or something like that, it would be a consideration. I don't know that it would be a deal breaker or not. I'm trying to think of a specific reason why oriented would be better on a refrac, but not really sure. Unless, like I said, unless you knew on the original completion all the holes were on the bottom of the pipe or something bizarre like that.
Okay.
So I'll add a quick comment from the perforating side.
Okay.
With the oriented. So one of the benefits that we see with the oriented perforating systems is you can obtain a much more consistent and specific hole size from your perforating design. Instead of trying to maintain a low percentage standard deviation at a wide variety of clearances, if you're shooting, say, 660, if you're only shooting up, you can really target a specific hole size that you want. And when you're only shooting in that same orientation, you can, typically get a much more consistent perforating hole size in that angle. So I think that helps narrow down some of those other variables that you see when you start to go to that oriented style perforating as well.
Okay. Well, speaking of,
There's a question on why people may be moving that way, and I would argue it's probably the people who have ran downhole cameras and have went and quantified the variation they're seeing in high side and low side holes. So I think 0-180 high side, low side is one of the most dangerous perf schemes to shoot, because we've seen, for example, in a 5.5 inch casing with 3 1/8 guns, a 0.42 inch design, we can see base holes as small as a 0.3 high side and 0.55 low side. So the variation can be pretty extreme. So that's part of the reason we like shooting the same orientation, 0 degree phasing. We've had the chance to work on multiple fiber wells, and as you know, we orient and shoot 180 degrees away from the fiber. So we discover a lot of optimizations shooting our perforations in this manner. It doesn't make sense for us to then go to the next well and shoot 60 degree phasing.
okay, if you're talking about 0 degree phase, 1 shot per cluster, Kyle, in that case?
I'd like fewer holes per cluster. Yeah, it doesn't have to be 1, but.
Okay. Well, let's say 1, maybe 2 shots per cluster. Do you think it's critical that if you're going to shoot that limited a number of holes, that you should pump acid or scour with 100 mesh sand? Is that a critical step?
I think the acid depends on the formation, and I don't even know if we consider 100 mesh a scouring agent anymore. We use it as our primary. So it'll be formation dependent for that, buddy.
Okay. Anybody else kind of have a standard practice on 0 degree phasing, especially 1 shot per cluster?
Go ahead.
I'd just jump in with this. I think a lot of people don't do oriented perforating because they're having to line the guns up with the newer machining practices and the disposable subs. They can machine the guns so that stuff will align without the individual gun alignment. But you see some people shoot straight up because of rock stress. You see other people worry about where the cement is, and they think maybe there's more stuff or more mud on the bottom of the pipe. But I do think you're going to see people shoot in other orientations for other reasons, because there's a lot of people shooting at 90 degree phasing. They shoot everything at they think the 3 and 9 o'clock positions, but if you really look at where the holes are in the pipe, they're more at the 4 and 8 o'clock positions. But I think there's going to be more and more reasons people want to know where the hole is in the pipe.
Okay. A question from one of the viewers, Dave or Kyle, what method are you using to orient your guns? I think Chris spoke on it briefly. Weight bar, something more advanced? How are you doing?
We're using a weight bar, buddy. We've also are working on something proprietary that some of our global wells guys have been testing, and I'm not at liberty to say what that is right now, but it's very efficient, cost effective, and we look forward to testing it out soon in our various business units. But we still plan on using a weight bar in combination with this new technique.
Buddy, we're like Dave, most of them are weight bars, but we're testing internal orientation. There's a lot of benefits to it. You can shorten your gun string. You're not worried about locking rings coming loose and guns rotating downhole. So we've seen a lot of potential in the internal orientation. Right now, the dependability is the biggest concern. When it's making its grounding contact inside the gun where it's rotating, we've had some issues where we lose contact and lose comm with the guns, but that's probably the orientation technology I'm most excited about.
Okay, great. Let's jump to a different topic here. Do you recommend, well, let's do another poll question. Let's do poll question number 5, the last poll question.
Well, here's the results from the last one first, buddy.
Okay, my bad.
No problem.
Optimum delta P for a given frac stage, 1,500 to 2,000 PSI. And one of the attendees felt like that was probably not the greatest question in the world because there's too many other details that would bear up on what that optimum delta P would be, and that's a good point. But at least as a starting point, in most applications, the audience seems to think anywhere from 1,000 to 2,000 PSI is going to be the right range. I think that's probably not too unusual to expect.
Which one did you want to do next? Number 5, the one about
Okay, yeah, let's do poll question number 5.
coming your way.
Does observed perforation directly relate to the amount of proppant that has been passed through it? I know that's been hotly debated. Okay. Let's think about that one. We'll come back to that answer here in a minute. Speaking of hole erosion, is hole erosion, as depicted by downhole cameras, is it a true representation of proppant distribution? And do production measurements in any way substantiate that? Have any design changes been shown that could maybe help equalize the observed erosion across all perforations? In other words, is there a way to mediate that? So first and foremost, panelists, does it really represent proppant distribution? And do you have production measurements to substantiate that? I know there's tracer data that addresses this, obviously camera data that addresses this, but it seems like there's been a struggle to try to get all of the data sets to corroborate one another. So
I think a piece of it,
okay.
I think
Kyle.
the sphericity and roundness of your proppant, the size of your proppant, which leads to the momentum, those things all impact how rapidly a hole erodes. So understanding the proppant specifically, the size and shape will impact how quickly it erodes. We have really nice examples where we've got downhole gauges on fiber wells. We're holding all chemicals constant, rate constant. We change from 100 mesh to 40/70, and we'll see a clear inflection on our treating pressure, and we'll see that erosion picks up, the rate of erosion picks up. I think on the diagnostic question, I haven't seen consistently where everything lines up. I have seen when you don't place anything in a cluster based on DAS and DTS, you don't have erosion and you don't have production. So I think at a high level, we've seen relationships, but if I put 10% more proppant into a cluster, I don't see 10% more production.
Is there any way to mediate that effect? You know, is there some design change that you could incorporate that would minimize the heel section being over eroded compared to the toe section, for instance? Have you seen anything that might mediate that effect? Anybody?
Well, I mean, Kyle just noted one thing, you know, the type of proppant. You're going to get less erosion with a nice round 100 mesh sand, sometimes much less than 40/70 or especially an angular 40/70. So there's a number of different characteristics, but particle size is certainly a key one. Particle size, as Phil could probably relate real well, is also important in terms of transport down the lateral. You're going to get less separation. You're going to be victimized by momentum effects. The proppant's going to tend to stay better with the water as it goes through the perforations. and correct me if I'm wrong, Phil. Phil's done some pretty extensive testing recently in this way. But yeah, of course there are things he can do. Getting just the right pressure drop, that's going to help. What is that? Well, that comes from not just computations, but trial and error, and you know, having a consistent way of looking at you know, pressure drop. Can't go in there with a camera all the time. Can do a step rate test all the time at the end of a job. So, you know, there are a number of things you can do, diligent people, to track how they're doing and to make adjustments.
Okay.
Hey, buddy, one thing that I would like to talk about too is
Yeah, Chris.
the distribution of the proppant. Like we were saying earlier that the rate per cluster might be different, but also the proppant concentration per cluster may be different. And proppant concentration, a higher proppant concentration might not directly correlate to more erosion. Sometimes the lower proppant concentrations may actually help erode better. If you draw a similarity to sandblasting or media blasting, the more angular grains, the harder grains, they're going to erode better. And there's also that sweet spot for how much medium do you want to put in that air flow rate to get the best erosion rates. One thing that we see in the Marcellus and Utica that's pretty interesting on proppant tracing projects is that a lot of times the heelmost cluster doesn't have the highest counts of proppant overall. For example, let's just say we had a 5 cluster stage. The heelmost cluster will have high counts, but it won't have the highest. Typically the highest counts will be the cluster that was the second from the heel, or maybe the third from the heel, because that flow rate finally gets slow enough to allow that proppant to turn the corner and go out through a perforation. Then after you have the cluster that has the highest counts, then it sort of like tails away towards the toemost clusters. So anyway, I think there's a lot more to be learned about the erosion rates and the proppant concentrations on each individual cluster too, and how that relates to the perforation.
I'll say something to kind of counter one of the things you just said. Years ago, we took a look at proppant volume versus erosion, proppant per perforation. It really seemed to be a function of volume. That we didn't see a lot of difference from 1 to 5 pounds per gallon. It didn't correlate well when we looked at concentration, but we took a look at overall proppant flow through, it seemed to correlate well. So at least within the normal concentrations that were run, I don't know that concentration, at least in terms of erosion, as a, you know, there's a significant difference. I haven't seen it, maybe missing something though.
Okay.
I'd like to jump in with just a couple comments.
Okay.
I think it's a big mistake to look at where the holes got the biggest and decide that's where also the proppant went. Velocity down the pipe matters, and everything's a function of the velocity down the pipe to some degree. If you look at it from the good work like School of Mines and Shaun are doing, you know, the fluid and the proppant probably don't travel together nearly as uniform as people think. And then on the erosion side and blind testing the cameras and the like, if an operator spends $100,000 running a camera, they'll pretty well believe the hole size the camera company reported, and that may or may not be true. I would say sometimes the hole size from a orifice flow equation are bigger than what the camera company may report to you. But I think they're very good on terms if they show one's bigger than another. So I believe the relative difference, but not maybe the absolute value. That would probably be a good comment as it relates to, you know, the camera data and erosion. But just because you have the biggest hole doesn't mean it took the most proppant. These other factors probably play in there. So I think, and then as it relates to the, you'll see the operator come back and say, you didn't shoot the hole size I wanted. But in reality, that may or may not be true depending on the gun system. But the one thing that is becoming more important, depending on the specific gun, is to understand under downhole pressure what size that perforating charge shoots, because most of the testing is done at surface conditions. And some of the under downhole conditions, some liners will shoot a different size hole. So that there's some really healthy dialogue going on with one guy saying the hole size isn't that, and that's making the shape charge manufacturers validate or check it at downhole pressures. So I think that's a key thing. But where all this is going to migrate over time as an industry is, I think it's going to migrate to the operator saying to the shape charge guy, I want this size hole in my casing, and then have that dialogue to really accomplish that goal, whether it's, a deep penetrating charge that shoots any size you want, but you orient to fix it or whatever. But for what the operator really needs to know is under his downhole conditions, what size hole does it really shoot? And there has to be some dialogue and some planning with the shape charge manufacturers to figure that out. And one of the reasons we're in the jam we are today is because a lot of this is the perforating is not planned out. And a lot of times it's between the wireline company and the shape charge manufacturer. So the more you have a three-way conversation that also involves the operator, I think that's probably healthy. But for most of the people on the phone, what they want to know is under their downhole conditions, what size hole do I have?
Okay, good. Backing up just a little bit, we had a comment on the chat line that one operator reports to have used Owen's internal orientation on a fiber project, and it worked very well to avoid the fiber. So there's a little tidbit I want to toss into the mix. Well, Phil, since you've gotten off on the subject of consistent holes, perforating, let's touch on that a little bit. The question is, it was asked by a number of different participants, has consistent entry hole perforating made a significant difference? And is it reasonable to expect that, and then get this is an extension, is it reasonable to expect that consistent hole size perforations will remain consistent throughout the entire length of the perforation tunnel? And will it help minimize perforation erosion problems? So who wants to elaborate? Shaun, you want to talk about that a little bit?
Yeah.
Consistent hole perforating, is it really that consistent? And is it reasonable to expect that you see that consistency throughout the entire tunnel?
So I think consistent hole charges have proven their value based on the amount of market that is now a consistent hole style charge versus a conventional SDP for the unconventionals. So I think people are definitely seeing the value in these consistent hole charges in their frac designs. As far as, is it reasonable that that tunnel diameter is going to stay the same the entire length? For most charges, it's always going to be charge dependent of what that tunnel geometry looks like. I will say for a majority of charges though, that tunnel diameter does taper off. Typically the harder the formation you're going into, the more it'll start to decrease in size. So again, it depends on what kind of charge you're starting off with, but I would say it's probably not reasonable to expect that a 1/2 inch diameter hole is going to stay a 1/2 inch diameter tunnel for 6 to 10 inches out into a shale formation. It's probably going to taper off. But one of the interesting things, like I think Dave mentioned earlier in the talk, was there's a lot of belief that the perforation tunnel isn't really contributing much. So is that perf tunnel tapering off really going to hurt you or not is another discussion, I would say.
Okay, good point.
Yeah, I'll say we've seen no evidence that tunnels are impactful, and so we don't care. about tunnel performance. We've told Shaun, you can use whatever gram weight you need to achieve the hole size through that casing that we want and that's consistent. So that's one point. I would say that the consistent hole size perforations aren't consistent enough, basing that off of numerous image surveys post-frac. And so that's a big reason why we love zero phase oriented perforating. You know, having a consistent fluid gap is going to help with consistency, even with consistent hole size perforations. So just wanted to chime in on those 2 points.
Okay. Speaking of hole erosion, we talked about whether or not the size of the hole is a true representation of the proppant distribution, and whether or not there's any production measurements to substantiate that. Does hole erosion, let's just assume that we really have limited ability to control the hole erosion, you know, once the frac starts, would you think that hole erosion or plug breaches that we know occur, are they compromising limited entry designs? Is that a significant issue? If you're really functioning around a limited entry design scheme, is this irregular, inconsistent hole erosion, maybe not perfectly uniform hole sizes? Does that kind of limit the benefits of limited entry designs?
So, buddy, we got a paper coming out. John Snider of ConocoPhillips is the primary author, talking about our experience in Eagleford. And we do touch upon production, but oriented zero phase high side perforating is definitely making a difference out there. And based on work we did 3-4 years ago before the group got sold on the idea of consistent hole size, we used to shoot oriented high side, and those wells outperformed the wells we did, which were quite a number, outperformed the typical well out there. So we'll talk about you know, aspects. Yeah, this stuff really does make a difference.
Okay, kind of a related question that has been presented. How close is too close to perforate next to a frac plug? Anybody have rules of thumb? How much distance should you put between the subsequent perforation and the frac plug? Any of your organizations have rules of thumb, or do you have a personal kind of a guideline on how you go about determining that?
I'd like to keep my cluster spacing consistent. So whatever it is between the stage, it should be the same between my heel cluster of the previous stage and my toe cluster of the new stage.
Okay.
Yeah, I'll say, buddy, you know, we've had some significant issues in one business unit with plug damage. And that's one of the wider cluster spacings that and some of that damage is related to momentum effects, the 40-70 mesh proppant moving past the first perforation cluster and banging into a fragile dissolvable plug. And that goes back to an unanswered part of the previous question. It matters a great deal, casing breaches, when they cause a loss of limited entry pressure, which we've seen from instrumented wells and studying DAS records, has a big impact on allocation when you really reduce your pressure drop to just a couple 100 pounds. And of course, you've got an outflow to some place you don't want that treatment going. So it's a horrible problem, and very important to get corrected. Once you get a big old eroded monster perforation, as you see sometimes in these surveys, that's a terrible thing too. And the big get bigger and bigger. So you need to do things, study your program, and avoid those, you know, things that create those monster perfs, as we have. I mean, at ConocoPhillips, you don't see a lot of monster perfs, outsized perforations in the numerous, you know, post-frac surveys that we do. So I'm really skipping back to that other question, thinking.
Oh, I'd like to just jump in and say one thing. It really, on these plugs, you know, the API's had subcommittees forever on perforating, but I'm really surprised the operators haven't set up a API subcommittee on frac plugs, because there's a lot of dirty little secrets on how plugs are tested or not. You know, just little simple things that, like, is the plug tested with the setting tool you're going to use in a horizontal position? So I think there's the operators, you know, right now they kind of take it at face value. If any service company tells you their plug's rated to 8 or 10,000, but it seems like the industry will slowly migrate to some kind of testing standards for both the dissolvable and the conventional plugs. What's acceptable leak rates? What, you know, are you testing it in water? Are you testing it in oil? So, you know, there's some really good questions to ask any service company on how do they test their plugs when they come in and tell you it's rated to some pressure rating. So not that downhole conditions can't cause plug failures too, but I think the industry has to head to some kind of API subcommittee to clean that area up.
Okay, let's look at our last poll results here. Derek? Does observed perforation directly relate to the amount of proppant that is passed through it? Well, there's certainly a little bit of an advantage in believing that that is the case. Some others have been very definitive about they do not believe that's the case, but with our audience, majority rules, they do believe that that is directly proportional to the proppant entry through those holes. Okay, let's try another topic here. Let's talk about limited entry. You know, we've got to get around to limited entry, extreme limited entry, et cetera. Obviously, that's a major topic these days. Several of you, tell us, do you recommend employing limited entry, extreme limited entry, engineered perforating, or a combination of the above? So in other words, when you get into your scheme, are you going to focus on extreme limited entry? Are you going to engineer the perforations? Are you going to use a combination of the two? And if you believe in engineered perforating, then what are you going to be targeting?
Buddy, we've got a poll question around that too. Do you want to do that now, or do you want to?
Okay, let them be thinking about that, and we'll put the poll question up first. Good idea. Which of these techniques is the best way to achieve engineered proppant coverage across the stage? Extreme limited entry, diversion, tapered perforating, and by that we mean 4, 5, 6 shots per foot as you go from the toe to the heel, for instance. Consistent hole size perforating, talked about that a little bit. Now we're talking about engineered perforating. In other words, you targeting some feature, some lithological feature, and just limited entry versus extreme limited entry. So which of these techniques, obviously I know you might prefer to check a combination of them, but just pick one and we'll see which one gets the majority of the votes here.
I'll let this run, buddy, while you guys discuss, and then when
yeah, we'll come back to that
question, we can show the results. Okay.
So back to that question. Limited entry, extreme limited entry, engineered perforating. What's your feeling about these options or combinations of these options?
Yeah, buddy, I'll say in general, 1,500 PSI is an initial perforation pressure drop targets, a pretty good one to me. So I guess that is not extreme limited entry perforating. I guess extreme in the eye of the beholder. Yeah, and of course you're going to drop from there just in your increase in discharge coefficient in that effect. But you know, we'd like to have something at the end of the day that's in the high hundreds, you know, 800, 900 PSI. You know, every situation's different, but that's a good general goal that we have that's worked, you know, pretty well. Engineered perforating, don't have much stock in it, very rarely, except for the most crude efforts apply it. Like if you see that you've porpoised into some dramatically different rock, well, you'd be wise not to mix rock types. or, but, you need to take some pause and think about it a little bit more. But yeah, geometric perforating is easy to do, more trouble-free, and usually works really well.
It sounds like you're coming from limited entry, not necessarily extreme limited entry, and not so much engineered perforating, more geometric. Is that about right?
Yeah, that's true.
Okay, how about the rest of you? Kyle, what would be your combination of those options?
Again, it goes back to what's the cost. If I'm trying to get to 2,000 because I saw it somewhere, but it's going to add a significant price tag to the frac, I agree with Dave. 1,500, if you can get there initially, is a good starting point. I think if you can maintain it, either through variable rate or maybe smaller proppant, I would rather have a consistent per friction, less the changing CD. Changing diameter is going to have a much bigger impact on losing our per friction than a changing CD. So 1,500 to 2,000 is normally where we're at.
One of the attendees is asking, okay, 1,500 PSI, do you consider that extreme limited entry?
I consider that normal limited entry.
Okay.
You get much below that, and with the inevitable erosion that you're going to have, even under the best conditions, where you're really watching it, like Kyle said, using round 100 mesh sand, that's a really advantageous move in reducing, perforation erosion. But yeah, you're still going to get erosive effects, and so yeah, that is a good number.
Okay.
I would tack on the equal hole size with the 1,500 plus PSI, like Dave said, his first answer. It's more important to have uniform hole size starting out than it is to try to get some design per friction based on what the vendor is telling you you're going to shoot. If you have 10 cluster design, 1 cluster shot low side and 9 are high side, there's a very high likelihood that that low side bottom of the hole perforation is larger from the very start of the stage. So it's going to accept more fluid, more proppant. It's going to erode more rapidly and become more dominant throughout that stage.
Okay. Anybody else?
Well, I'd say I probably would design in the 15 to 2,000 PSI range with a C sub V value of about 0.75, knowing it's going to go up, and I wouldn't shoot the same size holes in there, because I think one of the things that's coming out of a lot of these university studies is the proppant and the fluid don't travel uniformly together. So I think you're going to have to manage some things if you come to the conclusion that the proppants and the fluid don't distribute as evenly as you think. And that's maybe what I'd say from what I think I know.
So one of the attendees is asking, when you talk about a certain differential pressure, say 1,500 PSI, what C sub D do you have in mind? Or are you assuming?
We're running it with 0.75 at the start of the frac and growing it to 0.85 to 0.9 is about what we think it's at from, I'd say, the data that we have. So, and because the C sub D or C sub V value is a squared term, it has a little bigger impact than you'd think, but not necessarily compared to the diameter, the fourth power of the hole size, or diameter is to the fourth power, so it makes lots of differences. But I will say I think the orifice flow equation originally was developed was for the flow in the same direction, but if you're pumping the fluid by clusters, the velocity by that probably makes a little difference, but it's not a huge difference. So I think the orifice flow equation is still valid for that. But the other thing as it relates to erosion is, if you're eroding the hole itself, I think we probably have a lot more erosion behind pipe than we think, from some work we're doing with surface testing. We've eroded through a lot of steel. So I'd have to believe under downhole conditions, maybe we erode the hole out in the formation a little deeper than we ever thought.
Anybody else want to speak about C sub D, how it impacts these decisions?
Well, from step down tests, pre-prop and these tests are almost always subject to some significant uncertainty in pipe friction, unless you have bottom hole gauge somewhere. But we've seen discharge coefficients all over the place. I think Phil said this, but due to beveling of the perforations and what have you, even given the flow stream differences, 0.95 is typically what I'm using, something close to 1, figuring we're going to get something that's close to a nozzle. I'm coupling that also with some observations that Dynenergetics did under pressure, where they said they found that pressure with some back pressure, cavitation effects go, and they see their discharge coefficients trending after beveling to that high side, 0.95. So one might just use 0.95 as a good C sub D for doing their overall pressure drop calculations. So it's going to get there pretty quick once you start to have prop and beveling those perforation entry holes.
Okay. Another question that's been asked. Limited entry, we're talking about limited entry a bit here. Limited entry versus diversion. What are the pros and cons?
Entry.
Are they alternatives to one another, or would you use them in combination with each other? Go ahead, Kyle.
I think the main benefit is we have a lot more control over limited entry design. Diversion, in my opinion, you're trying to fix something that's broken, poorly designed initially. Based on fiber, we've seen a lot of variability in the outcomes of dropping diverter, where I think if we're focused on improving our consistency in our perforation size and placement, we'll be much better off in the long run.
So Kyle, tell me, what real-time changes do you make during the course of a frac stage if you sense that you're having some hole erosion issues, if you think you can determine that at the surface? What steps might you take? Might you, in that case, drop a diverter? Might you change the rate? Would you change the design? What real-time changes would you consider?
I think if you have available rate, that would be the only knob that you'd really go after to try to grab more rate. I wouldn't drop diverter. I've seen on fiber. So if you have a runaway perforation, you have a lot of erosion. I believe when you drop diverter, more times than not, it's probably going to restrict flow in your already weak clusters and make your dominant fractures more dominant. So, other real-time changes, if you have a high confidence you lost a plug early in the stage, you can make some decisions if you want to pump that full stage volume there or maybe cut it short. But I think real-time completions are in our future, and I think there's a lot of different tools that we need to couple to make real-time decisions along the lateral. We don't do it on a regular basis.
What about with your seal wellbore systems? Do you make any real-time changes there when you see you've communicated pretty strongly?
Yeah, we have, and we've only tested on a handful of stages, and what we did was we made those changes to an area where we had quite a bit of data. So we had an expected volume to arrival. If it arrives soon, the P50, we would reduce that stage volume. If it arrived after, we would pump the stage as designed. So very simple changes. It was more of a test to see what's the data transmission lag from field to office, and what's the communication pathway back to the PICs on location to make those changes. So again, in its infancy for sure, I think it's going to become a bigger part of our jobs in the future.
Okay, great. So gentlemen, if kind of talking about this communication issue, if you can make a case in a given frac stage that you've created super clusters that are taking the bulk of the frac treatment, is there anything you can do about it? Should you make changes based on that inclination, based on the pressure data from that well or the offset wells? If you think you created a super cluster, would you make any real-time changes at that point? Or maybe just change the design for the next stage accordingly?
Yeah, I think you change the next design, buddy. and sometimes these big pressure drops, they may not be super big perforations being eroded. There could be casing breaches, bridge plug failures. And in fact, in this one business unit I referred to previously, that's almost always what that problem is. So, addressing an outsized perforation size, we don't have the outsized perforation size. That's not the problem. So you got to be careful about your diagnosis.
Okay. This was a question that comes up from time to time, a little bit off the subject. How do you recommend perforating the toe most stage? What are the secrets to a successful toe stage perforating?
Yeah, I love to use the toe stage. Not everybody in ConocoPhillips agrees with me as a cleanup stage. So I wouldn't be doing limited entry. I'd be trying to maximize the flow area down there and just get that wellbore good and nice and cleaned up with acid and scour prop it and that type of thing. So that's the way I would like to, if it was my well, the way I'd like to handle it. And then I treat all the rest of the stages, essentially the same. Under
you, Chris?
the normal method.
You got any preferences about treating toe stages? You seen anything work better than others? Get that toe stage fracked successfully?
No, I think what Dave just mentioned is pretty standard in practice. Just use that toe stage to get rid of all the junk that's in the wellbore after it's been sitting from being cemented before being fractured, and don't try anything wild there. Just get that one in the ground and be happy with it, I guess.
Okay.
Yeah, I'd add, I think most people are running toe sleeves, right? So they're not perforating first stage. And I've seen a lot better result where they run two and walk the rate up slowly, because you never see the wiper plug company telling you that they can perfectly wipe 20-some thousand feet of pipe. So I think you're always leaving a little bit of cement in there. So my recommendation is run a couple toe sleeves and then do exactly what Cramer's saying, scour it. And it's not totally sacrificial, but it's partially that. And then most of the toe sleeve systems on the market have a restriction at the top, so you can use a ball instead of a bridge plug. So get rid of that bottom bridge plug sometimes too. But very high percentage of wells, I think they probably moved to toe sleeves.
Okay. All right. Well, we jumped around about a number of different options, approaches to perforating schemes. We talked about consistent hole size perforating. Seems to be some interest there. Maybe some question about how consistent they are, but our audience seems to think that's the way to go.
What did you the poll results from the last one?
Yeah, please. So the audience, we've asked this poll question in a number of these ProTech talks, and extreme limited entry usually wins the day. So I think there's reason to believe that extreme limited entry is here to stay. Consistent hole size perforating is an option. I think it's just a matter of can you provide production evidence to confirm that it's advantageous, or other forms of evidence to support it. And if so, it's certainly in principle makes a lot of sense. And if you can tie it to some equalization of erosion, that obviously is a plus for it. But in the meantime, extreme limited entry is still continues to win out on these polls. So back to my comment, we talked about consistent hole size perforating, seems to have some place here. We talked about oriented perforating. That seems to be coming back into vogue by basically the discussion we've had today. A couple of other things, and I know Phil is very familiar with one of them. What about propellant assisted perforating? And what about angled perforating? What do you see the future for these two perforating schemes? Are they flash in the pan, or is there still a market for these things? Does it look like, they're going to continue to grow?
Also, the angle perfs have some technical advantages that at least I'm aware of from things like erosion and proppant placement. I think you don't want to get the charges so far apart. I think keeping all your perfs close together helps you get the frac away. So I think that's important. The propellant systems could help with perf breakdown. You get to where they're mechanically complex. But I've seen where we've had some high clay content where you could throw everything in the kitchen sink to it and it still didn't help. But I do see that the propellant assisted perf, if you can keep it mechanically not all that complex, may have a home for sure.
How about the rest of you? Angle perforating, propellant assisted, you see a place?
Well, yeah, in fact, we're working with Shaun on a project and have high hopes of testing that out in Eagleford and elsewhere, trying the propellant technology as a means to get a more equal tortuosity amongst all perforation clusters, hoping that we get some significant extension cracks in the cement sheath or whatever to improve significantly injectivity in not just one, but all of our clusters. Perforating acid is something that has come on our radar lately, and we've done some trials with that where we have super inhibited 5% HCl acid. There's certain folks who market and supply that. And so where the wireline people are confident enough to have that acid in their wireline during pump down operations. So getting that acid displaced into that toe cluster, you just perforate the toe cluster, you have a ball on seat, then you've got acid spotted across the entire interval. Acid can actually be a nemesis towards equivalent tortuosity under a lot of conditions, but not if you spot it. So, that's another thing in addition to the propellant that we're interested in.
Hey, buddy, don't forget to add to your list frac plugs too, as you go through the different items that are of importance in this conversation. Because for one, somebody mentioned it here in the chat section about frac plugs, but that's also something that a successful plug and perf completion is based on, as your frac plugs. And buying the cheapest frac plugs that you can find might not always be the best solution, because there's been plenty of noted failures in proppant tracing diagnostics, and now the cameras and also dark vision are bringing that to light too. So the frac plug selection and placement is just as important as the perforations too, in the plug and perf treatment. And getting into the erosion too, there's been a lot of documentation on some of the damage that the erosion between the frac plug and the casing can do. So yeah, just wanted to have you add that to the list of things we covered.
Yeah, one of the attendees mentioned that there is a group looking at the development of testing standards for frac plugs. The group is called Advanced Well Equipment Standards, AWES, and it's facilitated by OTM Consultants. So that might be something that we might want to look into and see what they're learning there. Do we have any more poll questions? Have we covered them all, Derek?
I think we've got one more, and I know a couple of our panelists had to leave right at 2:30. Let me see which one we have left. We had one about clusters,
a little bit.
Clusters per stage, but if anybody needs to hop off, go ahead and do so. We appreciate your time, obviously, for coming today.
Definitely.
Thank you very much.
Thank you. If you need
Thank
to
you
run,
for the invite. Enjoyed it.
appreciate the time, fella. Great comments.
So if we want to do, we'll let Kyle run, and we can, the last poll question, I'll go ahead and throw it up real quick, and then we can,
Okay.
I won't leave it up for long. We can just, it's a semi-quick one anyway, so then we
How many
can.
clusters per stage do you think is ideal? 1 to 5, 6 to 10, 11, 15, 16 to 20, 20 plus. Okay, while you're voting on that, between you gentlemen, what do you consider to be the best cost-effective diagnostic technology for evaluating perforation efficiency? Again, with the emphasis on best and cost-effective. Obviously, there's a lot of science project type endeavors that you can undertake.
So the most
Routine kind of a
cost-effective-
surveillance technique, you know, what would be your 1 or 2 choices there?
I think the most cost-effective method is step-down testing, both before proppant and then after proppant at the end of a job. I mean, we always overflush these wells, and you can get a good step-down at the end of every single treatment. Again, the bottom hole gauge are subject to the tubing friction variations, but that's I think a especially good technique, more valuable in the beginning of a treatment, maybe than the end. I mean, you can get big, largely eroded perforations and only a few clusters open that will look like the same pressure drop as, less eroded clusters with all the clusters open. So you got to be a little bit cautious of that, but it's cost effective.
Okay. How about the rest of you? What's your choice? Good cost-effective diagnostic technologies, perforation efficiency.
I totally agree with, we're learning an awful lot off the step down tests before and after. And then it's maybe not quite on this, we're not gonna have time to it, but I would always probably chemical trace the toes for flow assurance over time. So I think that's a really good diagnostic that helps you at least understand production a little better. You know the whole thing's producing or not.
Yeah, but you don't have any bridges all the way out to the toe. That's nice to know. Okay, looking to the future. Shaun, maybe start with you. Where do you see the next step change in perforating technology to come from, and what impact do you think it will have? Where are we going with the Star Wars approaches here?
So what we've seen as of recent and kind of what we expect moving forward, going to these shorter clusters of 1 to 3 perforations per cluster. I think with all the data that's out there, trying to really focus in on getting a much more specific and very consistent performing perforator is probably where the next big thing is going to be. You kind of saw it shift with the consistent hole market. Everybody wanted around a 4.0, then it was a 4.2, then it kind of spread out to where most manufacturers have anywhere from like a 3.0 up to like a 5.0 or a 5.5. So there's a huge range of consistent hole charges now. I think as we start to go to these more specific oriented systems and fewer perforations, I think you're going to get very custom tailored products for these operators so they can target a very specific completion strategy. I don't think we're going to see kind of a one size fits all solution moving forward. I think you're going to have these guys like Dave that are going to really focus in on what works best for their specific application. And that's going to be the trend for different basins and different operators of what works best for them.
Okay, good. Okay, Phil?
I don't know of anybody doing this right now, and I'm not working on it, but it seems to me that if you look at the wireline systems that we're running in the field today that have a lot of electronics and digital switches, and I'm not an electrical guy, right? But it's pretty complicated, and you have to wonder at what point where we're doing this shoot on the fly stuff, if the gun systems will migrate to a more simplistic, for lack of a better word, I'll call it the slow burn fuse, where you get rid of all of these electronics and subs and you can just run one gun that does it all. Not saying I know how to do that, but if you look at how complicated we've made these guns from an electrical standpoint, with the people we have running them, it's scary it works as well as it does, honestly.
Okay, a couple of quick answers from the chat questions. Dave, step down test. How many steps should we have at the end of the stage? Think about that one for a minute. And one of the chat responses was, as far as the number of clusters, it depends on your casing size, the rate you have available. Otherwise, the more you can treat effectively in one stage, the better. I think that's a pretty darn good answer. So Dave, how many steps?
Oh, 3 to 4, buddy. I like to get at least 3. 4 is nice. 5 is overkill.
Okay. All right, one last question, and then we'll let everybody move on to their next meeting, if that's the way your days typically go.
Here's the poll results real quick, buddy, before you do that. Then just
What's that?
The poll results. Just
Oh, the poll results. Yeah, let's look at the last poll result.
There you go.
6 to 10. Looks like something in the neighborhood of 6 to 15 probably is getting to be optimum by most definitions. So I think that was a good comment about, again, so many of these questions have parameters that you have to factor in, and certainly casing size and rate, associated rates, is going to have a lot to do with this, but the more you can effectively treat in one stage, the better, especially from the economics side of things. Okay, thank you, Derek. Last question is going to be a quick flash round. So you're going to be given 10 seconds to consider each of the following 4 choices. Okay, so I'm going to give you a choice of this or that. Which do you prefer? One case, there's 3 choices. So no provisos, no assuming this or that. If you had to pick one of these right now, which route would you take? All right, number 1, we'll start with Shaun, since you're the first picture I see here. 0 degrees phase versus 9270 in general. Shaun?
I would go 0 degree.
Okay. Phil, 0 degree, 9270.
9270.
Dave?
0.
Chris?
0.
All right, looks like 0 wins out here. All right, the next quickie, next flash round. Got 3 choices. Dissolvable plugs, drillable plugs, plugless completions. I think I know which one person is going to vote for. All right, Shaun, dissolvable plugs, drillable plugs, plugless completions.
Not a strong preference. I'll go dissolvable.
Okay. Chris, jump ahead.
I've seen great success with plugless completions unless there's a supercluster development. So I'd stay far away from dissolvables, though, unless you can pressure test them for the amount of time it takes to pump a gun down and frack an entire stage. And if it can still hold pressure, then I'd give it a little bit of credibility. But I'd stay far away from dissolvables.
All right, you're violating the time limit here, Chris. It's all right. All right, Phil. Dissolvable, drillable, plugless.
I'm going to go drillable because I think you have so much sand left in the well, you got to clean it out anyway.
Okay. All right, back to Shaun.
You forgot
Somebody?
drillable.
Okay, Shaun. Tapered perforation scheme. In other words, 4, 5, 6 shots per foot as you go heel to toe. Tapered perforating scheme versus diversion.
I'd go tapered.
Okay. Chris?
Tapered as well.
Phil?
Reverse tapered.
654?
Probably more at the top.
More at the top, okay. All right, and the last flash round. For diagnostics, would you prefer RA tracing or chemical tracing? Shaun?
Whatever my buddy there, Chris, recommends.
Okay. All right, Chris, you're next. You get 2 votes.
I would say RH Racing for Shaun and myself.
All right. Phil?
RA Racing.
What's that?
RA.
All right, it's unanimous. Well, hey,
Hey, you're forgetting me, buddy.
oh, I'm sorry, Dave. Good night. I didn't see you.
Man,
Forgot about it.
RA.
All right. Thank you very much, fellow. Did I skip you on the other one? Tapered perforating versus diversion?
You did. Tapered.
Okay. Regular tapered? 4, 5, 6, or reverse tapered?
Yeah, regular.
Okay. Did I skip you on dissolvable plugs?
You did, but I blurted out drillable.
Okay, drillable plugs. We got 2 votes for drillable. Sorry about that. If I don't see your picture, I might have accidentally missed you there. Well, thanks very much, folks, for your participation, your invaluable contributions, the ideas that you put forth. Thank you for all the attendees. I'm sorry we couldn't get to every single one of the chat questions. We tried our best to cover most of them at least. Derek, you might step in and comment about what we're going to do with the recording, et cetera.
Sure. So we have it recorded today, and we will get it downloaded, edited, put together, and up, and we'll be posting that on our YouTube channel as well as on the ProTechnics portion of the Core Lab website. So we can send out a note afterwards when that link is ready, everybody. And then if you have any questions or if you don't see that link, please feel free to reach out to us either at Owen or ProTechnics. We will make sure to get you taken care of. So thanks for joining us today. We really appreciate it.
Yes, thanks very much, folks. Panelists, for spending time with us, and everyone be safe and do what we need to do to get this hurricane business past us. So look forward to hopefully visiting with you at the next ProTech Talks. Take care.